In my last video, I talked about how easy it is to use tasks within FreeRTOS and the benefits of breaking down problems into concurrent tasks. Some of my friends felt that I was being a bit abstract with how this is useful to you in the real world. Fair point. In this video, I'm going to show a practical example of how two PICOs communicate together using tasks to manage that communication. It's still a simple example and therefore not everything you might need to do in your project. What I'm basically doing is having one Pico generate a random number and send that to the second Pico. Both Picos will then display the random number on banks of 4 LEDs. Before I get started, please do remember to like and subscribe. I do appreciate it. I'm going to break down this communication pattern into a bridge of tasks or agents. We have our low-level comms services provided by the SDK or libraries, and we need to bridge that to our application. The first thing we need is something to manage our I/O, so to be able to read messages from the comms services before the buffer overflows, also to handle when messages are sent out. You may also see that agent doing services like keep alive messages to make sure the communication channel remains open. The messages that arrive need to be decoded. This will be some sort of protocol structure, and we will need to decode that to understand what has been provided, to discard junk which may occur due to issues with the connection. If we're sending data, then the data needs to be encoded into a protocol before it can be handed to our Manage I/O agent to send. Often we might want our application to have different messages or requests that it needs to handle. These might need to go to different parts of our application, so routing decisions are needed to decide where to send the request to get it answered. Generally, I provide action handlers that plug into my routing logic, so the router hands off the request to the action handler to process. That then interacts with the application logic itself. Of course, we often have lots of different actions, so the router is deciding which of these actions to pass the request to. We probably have some response going back from the action handler. Due to having lots of concurrent tasks going on, let's have a send queue to sequentialize messages being sent out. So this is a fairly standard pattern of tasks and supporting logic that I use to manage I/O in my devices. The sponsor for this video is PCBWay. PCBWay are a friendly manufacturer of PCBs to designs by people like you and me. PCBWay also offers services in 3D printing, CNC, sheet metal fabrication, and injection molding. To support the maker community, PCBWay are also hosting community project pages of great maker projects, so take a look at some of the examples there. Let's look at an example using the pattern in a very simple form. We're going to have two Picos with basic applications to blink an LED. Each Pico will have a bank of 4 LEDs, where it is displaying a number from 0 to 15. Then the Pico on the left, which I will call the conductor, will generate a random number between 0 and 15. It will display that number on its LEDs, then send it as a JSON message to the other Pico. The second Pico, the player, will receive a message, decode that message, and if valid, show the number on its bank of LEDs. We're basically going to design a set of components in FreeRTOS to handle this I/O pattern bridge. Firstly, I will have an I/O agent that will manage the serial communication from the UART on the Pico. I'm going to use polling as a strategy in this example, as it's simple. That means that this task constantly looks for new serial data. When it has a whole message, a line in this case, then the message will be passed to the decoder agent. The decoder agent will decode the JSON and check it's valid, so it has the number to display. In this example, I'm going to ignore the routing step because I only have one action to display the number on my LED. Then the action to display the number is done directly by the counter agent. Typically, this will be interfacing to parts of our application, but in this example, I'm getting to actually do this deed here. Finally, have a very dull application which just blinks an LED. So in terms of task breakdown, This is what our application is going to look like from the player's point of view, though we should also mention the services we'll use to let our tasks communicate. Our I/O agent is going to place the read message into a message buffer. This allows the message we are receiving to be variable length. Remember, the I/O agent isn't validating, it is just reading the data and passing it straight on to the decoder agent. The decoder agent has decoded the data so it can place it into a specific structure for the application. We can then place it in a queue for the counter agent to receive. In practice, I often hide these tasks, buffers and queues behind C++ classes to take a paradigm of active objects. For me, that makes the project simpler to conceive and therefore reduces the amount of mistakes I make. The code for this example is on GitHub as always. The example, of course, uses the Pico SDK and FreeRTOS Kernel libraries. It also uses a JSON parsing library by Rafa Garcia. He has an excellent little library which behaves beautifully on the Pico. From a hardware perspective, we really just need LEDs and a wire for the serial communication. Both Picos will have green LEDs on GPIO 0 to display the blink pulse LED. Then both will use 4 red LEDs on GPIO 2 to 5, which will be used to display the binary count value. Then GPIO 15 will be a blue LED which will display the mode of the device. It will be illuminated if the device is a conductor. We will connect pin 40 as 5V power between both devices. Also pin 38 as a common ground between the devices. Then we will use UART 0 on the Pico to communicate between the two devices. We can use GPIO 16 as transmit and GPIO 17 as receive, so the device on the right is the conductor. So an example, the unit on the right is the conductor and sending out the random sequence. When I pull the serial connection out, both units become conductors and start displaying different values. If you'd like to know more about FreeRTOS and all its capabilities to run tasks and communicate between them, then take a look at my FreeRTOS course for the Pico on Udemy's video training platform. For a few pounds, it will take you through the steps of FreeRTOS, the use of tasks and communicating between them, using semaphores, queues and message buffers. The I/O pattern I've talked about I use in Internet Protocol services as well. My IoT pattern, which I call Twin Things, communicates over MQTT. It uses FreeRTOS Core MQTT agent for I/O communication, then manages the MQTT session and decoding or encoding the protocol in an MQTT agent. Router's behavior checks for which action the request should be provided to. Often I have ping services as well as digital twin states that my IoT devices are managing. I talked through how to build up such a pattern and support IoT devices built on the Pico W on my IoT with Raspberry Pi Pico W course on Udemy. This is based around the FreeRTOS Core MQTT libraries and the basics of MQTT communications. The course covers connectivity on the Pico W to Wi-Fi and the basic use of sockets. These are what underpin MQTT protocol and allow us to publish and receive messages. FreeRTOS Kernel is really useful for helping to solve communication problems in an embedded system. These patterns come back time and time again in our development. I've placed the code for my example on GitHub to share, so please check that out. Please also check out my FreeRTOS and IoT courses on Udemy. I'll put the link in the description. Thank you very much for watching. Please do like the video as it helps others find it. Please subscribe and hit that notify button for more videos from me. Bye bye for now.